Here are some quick notes on star formation to accompany Chapter 2 of To Build a Star. So when you have a cloud of gas out in space, how do we decide whether it's going to collapse? Well, it's when the density in a certain region becomes large enough that collapse is going to be precipitated, and that's given by the so-called Jeans criterion. So if our cloud of gas were in equilibrium, if it were just constantly sitting there, not expanding or contracting, then it would satisfy virial equilibrium, where 2 times your kinetic energy is equal to minus the potential, which we talked about in the virial equilibrium quick notes. So the kinetic energy, this is 3 halves nkt, so the 3 halves is because you're in 3 dimensions. N is the number of particles in your gas cloud, and then you have the kT for the energy there. And the number of molecules in your cloud of gas is just equal to the mass of the cloud of gas divided by the average mass of a molecule. The potential energy part, what we need to do is figure out what's the potential energy contribution due to a given sort of slice of mass. So we want to integrate this, but we have an m and an r, little m and little r, that change together. We want to change this into just an integral over the mass coordinate, little m. So what we do is say, let's just have a constant density cloud of gas. It's close enough to true. Then what we can do is relate the radial coordinate to the amount of enclosed mass. That's little m. And if you look at this long enough, you can convince yourself that that relationship there is true. And so then the contribution to the potential for the everything inside a certain mass coordinate is given by this guy here. So then our potential energy, we just integrate that relationship for this slice of potential energy from 0 out to the total mass of the cloud, and we get that it's minus 3/5 newtons g times the mass of the cloud squared divided by the radius. And you might recognize this from electromagnetism. It's very similar to the potential from a uniformly charged sphere. So if we want to have collapse happen, we need the potential energy part, which is doing the pulling in, to counteract and overcome, in fact, the kinetic energy part, which would allow it to break apart. So potential has to overpower kinetic. So we can go ahead and plug in our relationships for our equations for the potential and for the kinetic energy into this inequality and get this business here. We're going to solve for the mass of the cloud. So basically keep mass on one side and move everything over to the other side of the inequality. And you get that the mass must be greater than this relationship, these constants, times the temperature times the radius of the cloud, which we refer to as the Jeans mass. Now, we really don't want to worry about what the radius of the cloud is. That seems like a weird thing to care about. We'd rather convert this into density. So take into account the fact that we have a constant density sphere. So the density is the mass divided by the volume, and the density is also going to be equal to the mass density is going to be equal to the number density times the average, the mean molecular weight of our gas cloud, of the molecules making up our gas cloud. So we can go ahead then and solve this relationship here for the radius and then plug that in to the Jeans mass formula, and we get this somewhat more complicated looking thing here. But you notice these are mostly constants, right? You have Newton's G, you have Boltzmann constant, you have the mass of hydrogen, and then your mean molecular weight. And so basically the only variables in here are the temperature and the number density. So you can go ahead and evaluate all those constants, and you find that you round a little bit, and rounding's fine because this is all approximate, that the Jeans mass is roughly 100 solar masses times the square root of the temperature of the cloud of gas cubed divided by the mean molecular weight to the 4th times the number density. And just to give you some numbers, so for some parts of our galactic disk where we see star formation occurring, we have diatomic hydrogen, so that means mu is actually 2. The environment is about 10 Kelvin, and the density is about 10 to the 3 molecules per cubic centimeter, which is pretty small. And you find the Jeans mass is about 25 solar masses. Now that doesn't mean that you've mostly formed 25 solar mass stars. These clouds actually tend to fragment, and then you form smaller stars than that, smaller mass stars. So some things that we can glean from this is that in the early universe, we know it was much hotter, and so that means that our first stars must have been more massive. So nowadays we form stars on the order of a solar mass. In the early universe, it must have been more like 100, 1,000 solar masses, very, very big stars. Now we also know that from the virial theorem that when our cloud collapses and it contracts, it heats up. Well, if it heats up, then the gene's mass becomes larger. So you need more density to collapse, so that at a certain point you'd stop collapsing if you didn't cool. So we know that cooling must happen for stars to form. So how does the cooling occur? The basic mechanism, right, is we need to convert kinetic energy, the motion of these molecules and the stuff inside the gas cloud, into radiation. And there's two ways to do this. So you can do this with molecules. So the molecules collide, and that then excites your molecule. So for instance, usually the main molecule we consider is carbon monoxide because it's the most prevalent. So you can excite the carbon monoxide via rotation, which is lower energy. At higher energies, you can go to vibration, and at the highest energies, you can go to electronic excitation. We're typically at lower energies, so we're mostly exciting rotational frequencies. So the collisions, they result in these carbon monoxide absorbing that energy and turning it into a rotation, and then that can then de-excite. And de-excitation happens via photon emission. And some fraction of these photons then escape the gas cloud, and it cools in this way. Now, gas clouds also consist of dust. So by dust, what do we mean is anything from a few molecules to like 100 microns or so of stuff stuck together. And here what happens is your molecules and your dust grains, collide together, and that causes the dust grain to get heated just from getting kind of smacked. And then it can radiate thermally. And this is only really relevant at higher densities when this can happen. So it's mostly going to be the CO cooling that is relevant for the cloud. Okay, so that point that we were talking about before, where the genes criterion is relevant, you're really talking about a free fall occurring. And this free fall time is given by the dynamical time, as we talked about in the dynamical quick notes. This is, relatively rapid. If you have an object like the sun, you're talking about like an hour. At a certain point, though, the cloud gets compact enough and it gets hot enough that you are dissociating the molecules. You're dissociating your diatomic hydrogen, and your cooling is going to be inefficient. And so our object is now, we finally call it a proto-star. So it's in hydrostatic equilibrium, but it's not yet fusing hydrogen in the core. So this is a proto-star. The energy of our protostar is going to be radiated away on this so-called Kelvin-Helmholtz timescale. So the only energy we have to release is the total energy, which by virial equilibrium is given by the gravitational potential, rather half of that gravitational potential. So as the protostar contracts, you're converting that potential energy into a luminosity that's being released. And so the time scale for this is roughly something like your gravitational potential, gm squared over r, divided by the luminosity of the object. And if you take the sun's mass and the sun's radius and the sun's luminosity, you find that this Kelvin-Helmholtz timescale is on the order of 30 million years. So Kelvin-Helmholtz timescale is a heck of a lot longer than the dynamical timescale, and that's one thing that lets you know that now your protostar is in hydrostatic equilibrium. So as far as how your protostar now evolves on the HR diagram, it's bright enough we can place it on the HR diagram. What it does is if we plot luminosity versus temperature as usual, with temperature increasing to the left, this protostar evolution is these somewhat vertical blue lines. Okay, and then the time scale, these are isochrones. The time scale is given by the red isochrones here. So how do we understand this sort of vertical descent on the HR diagram, at least for the cooler stars? Well, when we're seeing a star or a protostar, what we see is the surface. Okay, so the surface, what is that really? You know, stars are diffuse objects. It's really going to be the last place that a photon scatters. So when a photon, the last place that it scatters, that's known as the optical depth, and then it streams to you, to your eyeball or to your telescope, because that's where the surface is. If we have a sort of cool star, the envelope is convective, as we'll talk about a lot later, and so that means the radius is really large. If this radius were to expand a bit, if your radius is increased a little bit, then the temperature at the what we used to call the surface, it goes down a little bit. Okay, but this region near that surface, right? It's going to get it gets a bit cooler. It also gets a little bit thinner, right? Because you've expanded your radius, so now you have a slightly less dense region, and so then the optical depth is actually larger, right? So you're going to see deeper into the protostar. So what you see now, what's the new surface, is a bit deeper, and there the gas is actually still a little bit hotter, right? So it's kind of a swindle that the thing that you see as the surface is actually moving inwards. So what you used to call the surface is cooler, but the region you see is still about the same temperature as what you originally saw. Okay, so basically the effective temperature is roughly constant, and this is kind of the hand-wavy explanation for why your Hayashi track is what that's called, this evolution on the HR diagram. That's why your Hayashi track is roughly vertical. Now, actually proving this is something that we're capable of doing. It takes a lot more doing. You have to take into account the temperature dependence of the opacity. You have to take into account heat transport and what makes it convective, and so it's something we're not going to treat in these quick notes. But suffice it to say, if you're a cool star in this region of the HR diagram, then you'll follow the Hayashi track. And this is actually also why when you move off the main sequence and you do shell hydrogen burning and you have a red giant star, there you're also roughly moving vertically on the HR diagram because you have a convective envelope. The reason why you have these funky curves here, why it's not vertical as you go to these higher temperature and higher mass objects, is that now the heat transport isn't well described by convection, it's radiative, and so this gets different. It's more complicated, and it's something called the Henry track. But that's, again, something maybe for another day. So that is it for these quick notes on star formation.